Hi guys, another biochemistry video, finally on the study guide and finally kind of on lipids. So I've decided that I'm going to work through the study guide very quickly, a little bit, hopefully every night, and cover different parts of the study guide so this video can be chunked up into smaller groups so it's more digestible. So I'm going to start with lipids since that's something I haven't made a video on yet, and that's what I wanted to study the most tonight. So I'm just going to focus on the stuff that is in the study guide that the tutors provided, so you can kind of consider me a study guide. So without further ado, so the first bullet point is asking what lipids dissolve in. So if you're not sure, lipids dissolve in nonpolar solvents and not water, and that's directly from his PowerPoint. So what that means is lipids are nonpolar substances, and in chemistry we have a saying called like dissolves like. So that means nonpolar solvents are going to dissolve nonpolar substances, whereas polar substances will dissolve polar substances. So with that theory, our lipids are going to dissolve in other nonpolar substances. So a great example would be oil, but it will not dissolve in a polar substance such as water. So this is why when you put oil in water, it kind of separates because they can't dissolve in each other. Alright, so next up is the storage form of energy. So lipids have multiple functions. The primary function is going to be the storage of energy, and that is a special lipid called triacylglycerols. So not all lipids are energy storage, but triacylglycerols are a type of lipid, and those are the ones that are storing our energy. And I drew a nice generalized picture of what a triacylglycerol is over here. So a triacylglycerol is a glycerol molecule, and what makes it a glycerol molecule is that it's going to have 3 ester bonds, which I have highlighted in orange, bonding it to 3 fatty acid chains. So tri meaning 3, acyl referring to the functional group making up this glycerol, and glycerol referring to the fact that it's bonded to these fatty acids by ester bonds. So these ester bonds are going to be between the oxygen of the acetyl group and the carbon doubly bound to oxygen part of a fatty acid. And remember, R just means anything, so these fatty acid chains are these long carbon-hydrogen chains. Another function is that they are part of the cell membrane, and we're going to talk about this more later, but we call those our phospholipids. So a lipid that's in the cell membrane is a phospholipid. Next up, it's going to be a precursor to steroid hormone. So our lipid that is a precursor to steroid hormones is cholesterol. And then we can also combine lipids with other things to make a compound lipid. So compound, because it's a kind of like a compound sentence, it's 2 sentences put together. A compound lipid are going to be 2 different macromolecules bound together. So a phospholipid is going to be a lipid in a phosphate group. A glycolipid is going to be a sugar in a lipid. And a lipoprotein is going to be a protein in a lipid. It's as simple as, does it have lipo or lipid in the word? That would be a compound protein. So looking next at the chemistry of lipids, wasn't really sure what they were looking for at this bullet point, but some things that I think it could be referencing, first of all, is the number of carbons in the lipid are going to determine its property at different temperatures. So remember that if there are more than 12 carbons in the lipid, it's going to be solid at body temperature, so think butter. And then if there are less than or equal to 12 carbons, they're going to be liquid at, it says 0 degrees Celsius in his slide, so think oil. So the fewer the carbons, the more liquidy it's going to be. Something else I know contributes to the amount of liquidiness are double bonds. So this is referring to our saturated and unsaturated lipids. So unsaturated means it has a double bond because it is not fully saturated with hydrogen. So what does fully saturated with hydrogens mean? Let's draw in our ghost hydrogens. 1, 2, 3, 1, 2, 1, 2, 1, 2, 3. Versus if I had the same thing but without that double bond, we'd have 3 hydrogens at these 2 middle locations. So this is our unsaturated because it's not fully saturated with these hydrogens. So when we're looking at our unsaturated fatty acids, we have another thing we can look at, and that's cis versus trans, and that's just telling us the shape. So cis means same side, so if the different parts of the chain are sticking up on the same side, so on this example they're both up, that is cis. Versus here where they're going different sides. This one's going down and this one's going up, so that's trans. Trans meaning opposite or different. Alright, and before we move on, something else that we can bring up at this time is naming of carbons. So naming of carbons, the number of carbon atoms we have is going to give us a different prefix in our IUPAC naming system. So if you have 1 carbon in a compound, that's going to be a methane, 2 ethane, 3 propane, 4 butane, and so on and so forth. So when I'm saying methane, ethane, propane, and butane, I'm just meaning straight up carbon compounds. So this is a methane here because it has 1 carbon versus an ethane, which has 2 carbons. But we can use these same prefixes, and we're going to add a couple rules when we're naming our lipids or our fatty acids here in a few seconds. So moving on down, here we are at the naming system. So we're going to take those names from before, methane, ethane, propane, butane, pentane, ... And if we're trying to refer to a fatty acid, instead of the E, we're going to add oic and then acid. So examples from his slide, if you have butane, which is a 4-carbon compound, and it's actually a fatty acid, we're going to call it butanoic. So here's the OIC ending, and acid. Same with octane, octanoic acid. Alright, moving on. Food sources of fatty acids. This is where we're talking about, are the fatty acids essential or not? And the tutors told us we need to know that linoleic acid and alpha-linoleic acid are the essential fatty acids. So we need to consume these acids in our diet because we cannot make them ourselves. Just like how we have amino acids that are essential because we cannot make them ourselves. So linoleic acid is omega-6 and the alpha-linoleic acid is omega-3. So let's take a look more at what those mean. I'm going to skip this bullet point for a second. So here are 3 fatty acids that we've talked about. So this is your omega-3, omega-6, and omega-9. So let's think about what these words mean. So an omega-3 means we're going to use the omega naming system, and that the first double bond is on carbon 3. So when we are numbering carbons using specifically the omega system, we're going to start all the way over here on the left, and that is carbon number 1. This is the carbon numbering system just for naming omega fatty acids, not for any other method. So we have 1, 2, 3, and that's where we see our first double bond. And then in the omega system, we're going to have another double bond every 3 carbons after that. So you can see that 1, 2, 3 between those bonds. But just like, here, let's go through the other examples. So linoleic acid, or your omega-6, you have 1, 2, 3, 4, 5, 6, so that's your first double bond. And then in your omega-9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's how that works. That number after the word omega tells you which carbon the first double bond is on. As far as how many double bonds go, the more letters in the word, the more double bonds there will be. So linolenic has the most letters. There's 3 double bonds. Linoleic acid has fewer, so that has 2 double bonds. And oleic acid only has the 1 double bond. But we also need to be able to write these in the delta naming system. So I've already written an example down here. Linolenic, because it's a linolenic acid. 18, because there's 1, 2, 3, 4, 5, 6, 18 carbons making up the fatty acid chain. Colon 3, because there are 1, 2, 3 double bonds. This triangle telling us it's the delta naming system. And then the numbers that follow tell you which carbons the double bonds are on. So 3, 4, 5, 6. Hold on 1 second. Sorry, there was a typo. I had a 3 here originally, but it was supposed to be a 9. And you're going to see why that is. So in our delta naming system, we need to start at the beginning near the functional group. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is more similar to how we're used to naming carbons. So numbering the carbons is going to depend on if we're using the omega system or the delta system. Delta system, we start over here. Omega system, we're going to start over here. But these numbers are telling you where these double bonds are occurring. So we have 9, 10, 11, 12, 13, 14, 15 is where all those double bonds are. And then you can go through and do the rest of the examples on your own. These are just some problems associated with our essential fatty acids. So if you're not getting enough omega 3 and 6, which are your essential fatty acids, you're going to have, for a lack of omega-6, eczema and scaly skin. And for number 3, you're going to have some trouble concentrating. So if you're like me, you can't focus in biochemistry lecture, it's probably because you need some omega-3 fatty acids. Alright, moving on, HDL versus LDL. The tutors told us to focus on the fact that LDL is the bad cholesterol. So if there's something bad happening in the body, LDL. And that's what we find in our trans fats. And the reason it's bad is because it's bringing cholesterol to and dropping it off in different parts of the body where we don't need to have excess cholesterol. Good cholesterol is our HDL, H for happy, and it takes cholesterol out of the places where we don't need it. So if there's something good happening in the body, HDL. And once again, trans fatty acids, they're associated with our LDLs. So if we consume lots of trans fatty acids, we're going to raise those bad LDLs and lower the good HDLs. And that's what we find in the foods we love so much. I just had potato chips today, so sorry to my poor HDLs. Moving on, lipid peroxidation. So this is why our lipids spoil. They undergo lipid peroxidation. So when you put your food in the fridge, it goes rancid. It's because these free radicals are forming, or you might hear them referred to as ROS, reactive oxygen species. You do not want these, and you especially do not want them in your body. So if you have free radicals hanging out in your body longer than they should be, that's going to increase your membrane permeability and cause mitochondrial DNA damage. Pretty much not good stuff. Your body's going to start shutting down. So different processes in our body are going to produce some different types of free radicals. We need these processes to occur for energy production, yada, 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 but you might get these free radicals forming, so we need to get rid of them. that getting rid of them is called termination, and that happens because of antioxidants. So if you eat lots of blueberries, those blueberries are going to terminate these ROSs. But you don't need to eat tons of blueberries because your body can do it itself. For example, we have something called superoxide dismutase. So this is a type of antioxidant that your body naturally provides for you. He says this one is the most important. So this is not the only, but it is the most important. So what it does is it takes these reactive oxygen species, or our free radicals, and it converts them to hydrogen peroxide. That can occur in the mitochondria and the cytoplasm. Depending on where you are, there are different cofactors. So that is a manganese cofactor and a copper zinc cofactor. So mitochondria, cytoplasm is where we get hydrogen peroxide production, as long as you have these two different cofactors, respectively. And very quickly, lipid metabolism. So metabolism, chemical reactions that make food into energy. So that was easy, but there are some other things from his lipid transport module, mainly phospholipids. So know that there are two main types of phospholipids. You're going to have your phosphoglycerides and your sphingomyelins. So first of all, phospholipids have the same property. They're all going to be amphipathic, and that means they're going to be both hydrophobic and hydrophilic. So if I zoom in here, this is just a generalized phospholipid. We have this nice phosphate group up here with lots of carbon-oxygen bonds. Those are all polar bonds, so that's going to make this polar or hydrophilic. These tails are going to be your fatty acids. It's all going to be carbon and hydrogen, so those carbon-hydrogen bonds are nonpolar. Nonpolar means hydrophobic. So that is how they have both of these properties at the same time. That vocabulary word that you can use is amphipathic. So, like I said, phosphoglycerides are a type of phospholipids. You take all these things that we're used to. We had our glycerol right here, our two fatty acids right here, our phosphate group right here. But notice how there's an R up here. What makes a phosphoglyceride special is that it's going to have an alcohol group attached to it. And I'm so sorry, I could not find like a good picture of a phosphoglyceride, but here's another way of looking at it. Fatty acid chains, glycerol, phosphate, that's your P group. And an alcohol is an OH that would be attached to that. Sphingomyelin is another type of phospholipid. Sphingomyelin is down here. So sphingomyelin kind of looks similar to our phosphoglyceride. The biggest difference is it's going to have one fatty acid chain instead of two. So we can see down here just one fatty acid chain. It's also going to have a sphingosine structure, which we're going to talk about in a second, a phosphate group right here, and an amino alcohol, which is what you're seeing over here. So, what is this sphingosine? So a sphingosine is this structure right here. It's like this fatty acid chain, two alcohol groups, and an amino group. And this is where ceramides become important, because as soon as we add a fatty acid chain right here, that's what's going to make it a ceramide. So ceramides are important because they're going to become our sphingomyelins. They're going to be a precursor. So we can see that fatty acid residue chain here. That's going to take so this is our sphingosine, fatty acids, and here is the stuff that we added to our ceramide to make it a sphingomyelin. Alright, and then apoproteins' purpose. They transport proteins. And the big thing about apoproteins is that we mostly transport things in vesicles, which are just membrane-bound organelles, or just circles of these phospholipids that we were just talking about. But apoproteins, we have these big proteins on them. That's what makes it apo. Apo meaning on the outside, protein meaning protein, and these are signaling proteins. So when these apoproteins reach a special designation, these proteins can bind to a receptor, and that's how the body knows it's supposed to be there. Alright, so that's all I'm going to cover in this video. I'll get this uploaded, and then I will make another video on carbohydrates and another video on amino acids. I doubt I'll make one on minerals because you can probably do that with a flashcard. Alright, have a good night, guys.